Hello there, and welcome to Sleepy Answers. Tonight, we are drifting into one of the deepest mysteries that has ever puzzled human minds. A mystery so profound that philosophers have debated it for thousands of years, and scientists still struggle to fully understand it. We are exploring time itself. The invisible current that carries every moment of your life forward. The dimension you can never touch, never hold, never see, and yet it shapes absolutely everything you experience. Time sits at the center of existence. It flows through every breath you take, every thought that crosses your mind, every beat of your heart. Without time, there would be no change, no movement, no stories, no memories. The universe itself would freeze into a single eternal instant. Yet for something so fundamental to reality, time remains strangely elusive. You cannot point to it. You cannot catch it in your hands. You cannot slow it down when you need more of it, or speed it up when you wish a painful moment would end. As you settle in tonight, imagine time as an invisible river flowing all around you. You are floating downstream, watching the banks pass by. But unlike any river you have ever known, this one flows in only one direction, and you can never step into the same water twice. The moments that slip past you are gone forever, transformed into something we call the past, while new moments continuously emerge from something we call the future. And here you are, suspended in this razor-thin slice of existence we call the present, trying to understand what this river really is. If you enjoy these quiet journeys into the unknown, I invite you to like and subscribe. It helps others find their way here too, one sleepy soul at a time. And it lets me know that these explorations bring you some peace and wonder. But for now, all you need to do is rest. Let your eyes relax. Allow your body to soften. Let your mind drift gently as we begin to untangle one of the universe's most beautiful puzzles. Let us begin. The nature of time. What is it really? What is time? It seems like such a simple question. We all experience it every single day. We measure it with clocks. We plan our lives around it. We say things like, "I will see you in an hour," or "that happened yesterday," and everyone understands what we mean. Yet, when we try to define what time actually is, when we attempt to explain its true nature, we find ourselves grasping at something that keeps slipping through our conceptual fingers. Ancient philosophers wrestled with this question long before modern science emerged. In the 4th century, St. Augustine famously wrote that he knew what time was if no one asked him. But if he tried to explain it, he no longer knew. This captures something profound about time's nature. It is intimately familiar, and yet fundamentally mysterious. For most of human history, people thought of time as an absolute background against which events occurred. Time was like an invisible stage upon which the drama of the universe played out. It ticked forward at the same rate everywhere for everyone, regardless of what was happening. A second in Rome was exactly the same as a second in China. An hour for a person standing still was exactly the same as an hour for someone running. This view seemed perfectly sensible based on everyday experience. Isaac Newton formalized this intuition in his laws of physics. He described time as flowing equably without relation to anything external. In Newton's universe, time was like an invisible clock that existed independently of matter, space, and energy. It marched forward at a constant rate, never speeding up, never slowing down, providing a universal framework for measuring change. But this comfortable understanding would not survive the 20th century. In the early 1900s, a young patent clerk named Albert Einstein began thinking deeply about the nature of light and motion. He performed thought experiments, imagining what would happen if you could ride alongside a beam of light, or if you watched clocks from different moving perspectives. What he discovered through these mental explorations would shatter the Newtonian view of time forever. Einstein realized that time is not absolute. It is not the same for everyone. Two people moving at different speeds will actually experience time passing at different rates. A clock on a fast-moving spaceship will tick more slowly than a clock sitting still on Earth. Time, Einstein showed, is relative. It depends on your motion and your position in a gravitational field. This revelation transformed our understanding of reality itself. Time was not a separate stage upon which the universe played out. Instead, time was woven together with the fabric of space into a single unified entity that Einstein and his contemporaries called space-time. Just as you cannot separate length from width from height when describing space, you cannot separate time from the three spatial dimensions when describing the universe. But what does this really mean? What is time made of? Is it a substance? Is it a field? Is it a dimension like length and width and height? The truth is that physicists still debate this question. Some argue that time is fundamental, that it is a basic feature of reality that cannot be reduced to anything more basic. Others suggest that time might be emergent, arising from deeper, more fundamental processes that do not themselves involve time. Still others wonder whether time might not be real at all, but rather an illusion created by the way our brains process information. One way to think about time is as a dimension, similar to the spatial dimensions we are familiar with. When you describe where something is, you need three numbers. You might say an object is 5 meters to the left, 3 meters forward, and 2 meters up. Those three numbers specify a location in three-dimensional space. But to fully describe when and where something happens, you need a fourth number, the time. You need to say not just where the object is, but when it is there. This is why physicists sometimes call time the fourth dimension. It is an additional coordinate you need to specify events completely. If someone asks you where you were when something important happened, you do not just say, "I was in New York." You say, "I was in New York on the corner of 5th Avenue and 2nd Street on November 21st at 3 in the afternoon. The location in space and the location in time together define the event. Yet time feels different from spatial dimensions. You can move freely in space. You can go left or right, forward or backward, up or down. But in time, you seem to move in only one direction. You travel from past to future, never the reverse. You remember yesterday, but not tomorrow. This asymmetry makes time feel fundamentally different from space, even though they are woven together in the fabric of space-time. Part of what makes time so puzzling is that it seems to exist at multiple levels. There is the time measured by clocks, which physicists can describe with precise mathematical equations. There is the time we experience psychologically, with its strange ability to seem to speed up when we are having fun and slow down when we are bored. There is the cosmic time associated with the expansion of the universe, stretching back nearly 14 billion years to the Big Bang. And there may be quantum time, operating at the smallest scales of reality, according to rules we barely understand. All of these aspects of time are connected, yet they each present their own mysteries. Throughout this journey, we will explore these different faces of time, trying to understand what this invisible dimension really is, why it flows in one direction, how it can stretch and compress, and whether the past and future are as different as they seem. Time as the fourth dimension. To understand time as a dimension, we need to step back and think about what dimensions actually are. In everyday language, we talk about living in a three-dimensional world. We can move left and right, forward and backward, up and down. These three independent directions give us the freedom to navigate through space, to arrange objects, to build structures, to travel from place to place. But dimensions are really just independent directions of freedom. They are the different ways you can vary something without changing anything else. When mathematicians and physicists talk about dimensions, they are talking about the minimum number of coordinates you need to specify something completely. For a long time, people thought three spatial dimensions were all that existed. The universe was a three-dimensional stage, and time was just a clock ticking in the background. But Einstein's theories showed that this picture was incomplete. Time is not separate from space. The two are intimately connected, woven together into a four-dimensional fabric called space-time. The person who first clearly articulated this idea was Hermann Minkowski, one of Einstein's former mathematics professors. In 1908, Minkowski gave a famous lecture in which he declared that henceforth space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union between the two would preserve an independent reality. This union became known as Minkowski spacetime. In Minkowski's picture, every event in the universe can be specified by four coordinates. Three spatial coordinates telling you where it happened, and one time coordinate telling you when it happened. A point in this four-dimensional spacetime is called an event. Your entire life, from birth to death, traces out a curve through spacetime called a world line. Every moment of your existence is a different event, a different point along this four-dimensional path. This might sound abstract, but it has profound implications. In three-dimensional space, the distance between 2 points is given by a formula you probably learned in school. If one point has coordinates x1, y1, z1, and another has coordinates x2, y2, z2, the distance between them involves the square root of the sum of the squares of the differences in each coordinate. In space-time, there is an analogous concept called the interval, which combines differences in space and differences in time. But here is where time reveals its strange character. In the space-time interval, the time component enters with a minus sign compared to the spatial components. This mathematical detail has enormous consequences. It means that time really is different from space in a fundamental way. The geometry of space-time is not like the geometry of ordinary three-dimensional space. It has a different structure, one that gives time its special character. This difference shows up in many ways. In ordinary space, you can rotate your coordinate system. You can turn your x-axis into your y-axis by rotating 90 degrees. But in space-time, you cannot rotate a purely spatial direction into a purely temporal direction. Time remains distinct. Yet motion does mix space and time together. When you move through space, you are also moving through time. And the faster you move through space, the slower you move through time. This is the heart of Einstein's special theory of relativity. There is a cosmic speed limit, the speed of light, and as you approach this limit, time dilation becomes extreme. A clock moving close to the speed of light ticks much more slowly than a clock at rest. This is not an illusion. It is not a trick of observation. Time genuinely passes more slowly for moving objects. If one twin travels in a fast spaceship while the other stays home, the traveling twin will age more slowly. When they reunite, the traveler will be younger than their sibling who stayed behind. This is the famous twin paradox, though it is not actually a paradox once you understand space-time properly. Einstein's general theory of relativity takes this even further. In general relativity, gravity is not a force in the traditional sense. Instead, mass and energy curve the fabric of space-time itself. Imagine placing a heavy ball on a stretched rubber sheet. The ball creates a depression, and if you roll a smaller ball nearby, it will curve toward the larger one, following the curved surface of the sheet. This is similar to how planets orbit the Sun. They follow curved paths through space-time created by the Sun's mass. But the curvature affects not just space, but time as well. In a strong gravitational field, time runs more slowly. A clock near a massive object ticks more slowly than a clock far away from any mass. This effect has been measured with atomic clocks at different altitudes. A clock at the top of a mountain runs slightly faster than a clock at sea level because it is slightly farther from Earth's center and experiences slightly weaker gravity. Near extremely massive objects, time dilation becomes dramatic. Near a black hole, time slows down so much that, from the perspective of a distant observer, it appears to nearly stop at the event horizon. An astronaut falling into a black hole would experience time normally from their own perspective. But to someone watching from far away, the astronaut would appear to slow down and freeze, taking forever to cross the event horizon. This interweaving of space and time into space-time reveals something profound about the universe. Events do not happen in space at different times. Events happen in space-time. The past, present, and future all exist in space-time as different regions, different coordinates. This view suggests that, in some sense, all moments of time exist on equal footing. The past has not vanished. The future has not yet come into being. They are all part of the eternal four-dimensional structure of space-time. This idea troubles many people. It seems to conflict with our deep intuition that the present is special, that now is real in a way that past and future are not. We feel that the past is fixed and gone, while the future is open and yet to be determined. But in the space-time picture, this distinction loses its clarity. From a perspective outside of time, looking down on all of space-time at once, past, present, and future, are all equally real, like different locations in space. Some physicists and philosophers embrace this view, called the block universe or eternalism. In this picture, time's flow is an illusion created by our consciousness moving through space-time, experiencing one slice of the block universe after another. Others reject this view, arguing that the present is genuinely special and that the passage of time is real. The debate continues. But what is clear is that time, whatever it ultimately is not the simple, universal, absolute ticking clock that Newton imagined. It is a dimension of the universe, interwoven with space, flexible and relative, curved by mass and energy, and fundamentally woven into the fabric of reality itself. The arrow of time. Time does not just exist. It flows. It moves. It has a direction. You remember yesterday, but not tomorrow. Eggs break, but do not spontaneously reassemble. Coffee cools down, but does not spontaneously heat up. Everywhere you look, there is an asymmetry between past and future. This asymmetry is called the arrow of time. The arrow of time is one of the deepest mysteries in physics. Most of the fundamental laws of physics do not distinguish between past and future. If you filmed a billiard ball collision and played the video backward, the reversed motion would obey the same laws of physics as the forward motion. At the microscopic level, the equations of physics are mostly time-symmetric. They work just as well forward as backward. Yet the world we experience is not time-symmetric. We can tell the difference between a film played forward and a film played backward. If you see a film of a glass falling off a table and shattering on the floor, you know that is the correct direction. If the film shows shattered glass pieces jumping off the floor and assembling into a whole glass that then flies up onto the table, you know the film is running backward. Why? What makes time have this arrow? What breaks the time symmetry of the fundamental laws to create the asymmetric world we experience? The answer lies in a concept from thermodynamics called entropy. Entropy is often described as disorder or randomness, though these are imprecise characterizations. More accurately, entropy is a measure of the number of microscopic arrangements that correspond to the same macroscopic state. Imagine you have a room with air molecules. If all the molecules are bunched up in one corner, that is a very specific low entropy state. There are relatively few ways to arrange the molecules so that they are all in that corner. But if the molecules are spread evenly throughout the room, that is a high entropy state. There are countless ways to arrange the molecules so that they are evenly distributed. The system naturally evolves toward states with more possible arrangements, which means it evolves toward higher entropy. This is the second law of thermodynamics. In an isolated system, entropy tends to increase over time. Order tends to turn into disorder. Concentrated energy tends to spread out. Differences tend to even out. The universe constantly moves from lower entropy states to higher entropy states. And this is the thermodynamic arrow of time. The direction of time points in the direction of increasing entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. You can tell which direction is forward in time by asking which direction entropy increases. This explains why many everyday processes are irreversible. When you drop a glass and it shatters, entropy increases. The organized structure of the glass breaks down into disordered fragments. Heat spreads out into the environment. The system moves to a higher entropy state. The reverse process, where scattered glass fragments spontaneously reassemble, is not impossible according to the fundamental laws of physics. But it is so fantastically improbable that it never happens. The number of ways for the glass to be shattered is vastly larger than the number of ways for it to be intact and sitting on the table. When coffee cools down in a room, heat energy flows from the hot coffee to the cooler air. This increases entropy because the energy becomes more spread out, more evenly distributed. The reverse process, where heat flows from cool air into the coffee to warm it up, would decrease entropy. Again, this is not forbidden by the fundamental laws, but it is so improbable that it never occurs. The connection between entropy and time is profound. Our experience of time passing, of moving from past to future, may be fundamentally connected to the universe's journey from low entropy to high entropy. We remember the past, but not the future, because memories require changes in our brain that increase entropy. The very act of recording information, of forming memories, increases the entropy of the universe. This means that memory can only work in one direction, the direction of increasing entropy, which we call the future. Some physicists, including Stephen Hawking, have argued that all the other arrows of time ultimately reduce to the thermodynamic arrow. The psychological arrow of time, our subjective experience of time flowing from past to future, exists because our brains are thermodynamic systems that increase entropy as they form memories. The cosmological arrow of time, associated with the expansion of the universe, may be related to the thermodynamic arrow because the early universe was in a very low entropy state. But this raises a puzzle. If entropy always increases, and if it has been increasing throughout the history of the universe, then the universe must have started in an extremely low entropy state. The Big Bang must have been a moment of extraordinarily high order, incredibly low entropy. Why? What made the initial state of the universe so special? This is called the problem of the low entropy past. It is one of the great unsolved questions in cosmology. The standard Big Bang model describes how the universe expanded from an extremely hot, dense state. But it does not explain why that initial state had such low entropy. Without an explanation for this, the arrow of time remains somewhat mysterious. We can describe how entropy increases and how this gives time its direction, but we cannot fully explain why the universe started in a low entropy state that allowed entropy to increase in the first place. Some cosmologists have proposed answers. Perhaps the Big Bang was not truly the beginning. Perhaps there was something before it, and the low entropy state emerged from some earlier process. Perhaps there are many universes with different entropy histories, and we find ourselves in one with low entropy in the past simply because that is the kind of universe where conscious beings like us can exist. Perhaps the laws of physics contain some deeper principle that explains the initial conditions. The debate continues. But what is clear is that the arrow of time, the asymmetry between past and future that we take for granted every single day emerges from the statistical behavior of countless particles following laws that are themselves time-symmetric. The arrow is not inscribed in the fundamental laws. It emerges from the improbable initial state of the universe and the statistical tendency for systems to evolve toward more probable, higher entropy states. This means that, in principle, time could flow differently. If the universe had started in a high entropy state, there would be no arrow of time. The future would not be distinguishable from the past. Processes would be reversible. Memory would not exist. Cause and effect would lose their meaning. The universe would be a timeless chaos, with no clear direction to the unfolding of events. We live in a universe where time has an arrow only because we live in a universe that started in an improbable, low-entropy state. The flow of time that you experience, the progression from past through present to future, the accumulation of memories, the irreversibility of events, all of these aspects of temporal experience trace back to that mysterious initial condition at the dawn of the cosmos: time, dilation, and relativity. One of the most mind-bending consequences of Einstein's relativity is that time is not universal. It does not pass at the same rate for everyone. Depending on how fast you are moving and how deep you are in a gravitational field, time can stretch and compress, speed up, and slow down. This phenomenon is called time dilation, and it is one of the most thoroughly tested and confirmed predictions in all of physics. The first hint of time dilation comes from special relativity, Einstein's theory of space and time in the absence of gravity. The theory rests on two fundamental principles. First, the laws of physics are the same in all inertial reference frames, meaning for all observers moving at constant velocity. Second, the speed of light in vacuum is the same for all observers, regardless of their motion. That second principle is the strange one. In everyday experience, speeds add. If you are on a train moving at 50 miles per hour and you walk forward at 3 miles per hour, someone standing by the tracks would see you moving at 53 miles per hour. But light does not behave this way. If you are on a spaceship, moving at half the speed of light, and you shine a flashlight forward, someone at rest would not see the light traveling at 1.5 times the speed of light. They would see it traveling at exactly the speed of light, the same speed you measure on the spaceship. This constancy of the speed of light forces time and space to be flexible. If observers in different reference frames all measure the same speed for light, then they must disagree about distances and durations. What one observer measures as a meter or a second will be different from what another observer measures. Time dilation is the result. If you watch a clock moving relative to you, it will tick more slowly than your own clock. This is not because of any mechanical defect in the moving clock. It is because time itself passes more slowly for the moving clock. All processes slow down. Mechanical clocks, atomic vibrations, heartbeats, thoughts, everything. The amount of time dilation depends on speed. At everyday speeds, the effect is negligible. If you drive in a car for an hour, your watch will lag behind a watch that stayed home by only a few billionths of a second. Far too small to notice. But as speeds approach the speed of light, time dilation becomes dramatic. At 90% of light speed, time slows by more than half. At 99.9% of light speed, a moving clock ticks about 22 times slower than a stationary clock. This effect has been confirmed countless times. Unstable particles created in accelerators live longer when they are moving at high speeds. Atomic clocks flown around the world on airplanes show measurable differences from clocks that stayed on the ground, exactly as relativity predicts. The global positioning system in your phone would not work without accounting for time dilation. The satellites orbit at high speeds and experience weaker gravity than clocks on the surface, both of which affect their clocks. Engineers must include relativistic corrections, or GPS would accumulate errors of several miles per day. The twin paradox illustrates time dilation dramatically. Imagine identical twins. One stays on Earth, while the other travels to a distant star and back at near light speed. For the traveler, the journey might take 5 years. But when the traveler returns home, they find that decades have passed on Earth. The stay-at-home twin has aged much more than the traveler. This is not science fiction. It is a real consequence of relativity. Clocks in motion tick slowly, and biological aging is just a kind of clock. Some people find this paradox puzzling. They wonder why the traveling twin ages less rather than the stay-at-home twin. After all, from the traveler's perspective, Earth was moving away and then moving back. Should not the Earth twin be the one who ages less? The resolution is that the situation is not symmetric. The traveling twin accelerates to turn around and come back. They change reference frames. The stay-at-home twin remains in a single inertial frame the whole time. This asymmetry breaks the symmetry of the problem and explains why the traveler ages less. General relativity adds another layer to time dilation. In Einstein's theory of gravity, massive objects curve space-time, and this curvature affects the flow of time. In a gravitational field, time runs more slowly. The stronger the gravity, the slower the time. This gravitational time dilation has also been measured. Atomic clocks at different altitudes run at different rates. A clock on a mountaintop, farther from Earth's center, runs slightly faster than a clock at sea level. The difference is tiny, only a few parts in a trillion, but modern atomic clocks are precise enough to detect it. Near extremely massive objects, gravitational time dilation becomes extreme. Near a neutron star, where gravity is millions of times stronger than on Earth, time slows dramatically. Near a black hole, time dilation becomes infinite at the event horizon. A distant observer watching something fall toward a black hole would see it slow down and appear to freeze at the horizon, never quite crossing it, because time at the horizon has slowed to a standstill relative to the distant observer. Yet, from the perspective of something falling into the black hole, nothing special happens at the horizon. Time passes normally. The object crosses the horizon in a finite time and continues falling toward the singularity at the center. The dramatic time dilation is relative. It depends on your reference frame. This relativity of time troubles some people. It feels wrong that time could pass at different rates in different places. We are accustomed to thinking of time as universal, as a cosmic metronome ticking at the same rate everywhere. But relativity shows that this intuition is false. Time is local. Each observer has their own time, their own clock, and different observers in different states of motion or at different positions in gravitational fields will measure different amounts of time between the same two events. This does not mean time is subjective or arbitrary. The relationship between different observers' times is governed by precise mathematical laws. If you know the motion and position of two observers, you can calculate exactly how their clocks will compare. Relativity does not say anything goes. It says that time is relative, not absolute. One way to think about this is that there is no single universal now. Events that are simultaneous for one observer may not be simultaneous for another. What you consider to be happening right now on a distant planet depends on your state of motion. Change your velocity, and the set of distant events that are in your present moment changes. This relativity of simultaneity is perhaps the most philosophically disturbing aspect of relativity. It suggests that the present moment, the now that feels so real and special, is not an objective feature of the universe. It is observer-dependent. Different observers slice space-time into past, present, and future in different ways. Yet despite all this relativity and flexibility, space-time as a whole has an objective structure. The interval between two events, which combines space and time, is the same for all observers. Different observers may disagree about the distance in space and the duration in time between two events, but they will agree on the space-time interval. This invariance is what makes relativity a theory about objective reality rather than mere subjectivity. Time dilation also opens the door to a kind of time travel. By moving at high speeds or spending time in a strong gravitational field, you can effectively travel into the future. When you slow down or move away from the massive object, you will find that more time has passed for the outside world than has passed for you. Astronauts on the International Space Station age slightly more slowly than people on Earth because they are moving fast and experiencing slightly weaker gravity. The effect is minuscule, only a few milliseconds over months in orbit, but it is real. In principle, you could build a spaceship that accelerates to near light speed, travels for what feels like a few years to you, and then returns to Earth to find that centuries have passed. You would have traveled to Earth's future without aging much yourself. This is allowed by the laws of physics. The only obstacles are technological. We do not currently have the energy sources or engineering capabilities to accelerate massive objects to near light speed. But travel to the past is a different matter. Nothing in relativity allows you to travel backward in time. You can slow your clock relative to others, effectively jumping forward in time. But you cannot reverse the process. The arrow of time remains one-directional. Causes precede effects. You can visit the future, but not the past. Quantum time. At the smallest scales of reality, in the realm of quantum mechanics, time becomes even stranger. Quantum mechanics is a theory that describes the behavior of atoms, electrons, photons, and other fundamental particles. It is one of the most successful theories in physics, making predictions that have been confirmed to astounding precision. Yet, it presents deep puzzles about the nature of time. In classical physics, time is a parameter that labels when things happen. You can write down equations that describe how a system evolves over time. If you know the state of the system at one moment and you know the laws of physics, you can in principle calculate the state at any other moment, past or future. Time is like a coordinate, an independent variable against which everything else changes. Quantum mechanics keeps this basic structure. The Schrödinger equation, the fundamental equation of quantum mechanics, describes how a quantum state evolves over time. But the content of that evolution is deeply strange. In quantum mechanics, particles do not have definite positions and velocities. Instead, they exist in superpositions, simultaneously occupying many states at once until they are measured. Before you measure a quantum particle's position, it does not have a definite position. It has a wave function that describes probabilities for different positions. When you measure it, the wave function collapses and the particle suddenly has a definite position. This collapse is instantaneous. It does not take time. One moment the particle is in a superposition. The next moment it has a definite value. This introduces a puzzle about time. If the collapse is instantaneous, does that mean quantum mechanics violates relativity, which says that nothing can happen instantaneously across space? If two particles are entangled, meaning their quantum states are correlated, and you measure one, the collapse of the wave function instantly affects the other particle, even if it is far away. Does this allow faster-than-light communication? Does it require a universal notion of simultaneity? These questions have troubled physicists for nearly a century. The consensus is that wave function collapse does not allow faster-than-light signaling because the measurement outcomes are random. You cannot control what result you get, so you cannot use it to send information. But the instantaneous nature of collapse remains philosophically puzzling. Some interpretations of quantum mechanics avoid the problem by denying that collapse really happens. In the many worlds interpretation, the wave function never collapses. Instead, when a measurement occurs, the universe splits into multiple branches, one for each possible outcome. Each branch contains an observer who sees a definite result. From inside any branch, it looks like collapse occurred, but from a God's eye view, the entire wave function continues to evolve smoothly according to the Schrödinger equation. In many worlds, time is less mysterious. It is simply a parameter describing the evolution of the universal wave function. But the interpretation introduces other puzzles. What does it mean for the universe to split? How do we make sense of probability if all outcomes actually occur? These questions are still debated. Other interpretations take different approaches. Some argue that collapse is a real physical process that needs to be added to quantum mechanics. Some suggest that the wave function does not represent reality itself, but only our knowledge of reality. The variety of interpretations reflects the deep difficulty of understanding what quantum mechanics tells us about time and reality. One aspect of quantum mechanics that definitely affects time is the uncertainty principle. In quantum mechanics, certain pairs of properties cannot both be precisely defined at the same time. The most famous example is position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. There is also an uncertainty relationship between energy and time. The more precisely you confine an event in time, the more uncertain its energy becomes. This has strange consequences. In quantum field theory, even empty space is not truly empty. Pairs of particles and antiparticles constantly pop into existence and then annihilate each other in tiny fractions of a second. These virtual particles exist because the uncertainty principle allows temporary violations of energy conservation over very short time intervals. This quantum foam suggests that at the smallest scales, time itself might fluctuate and become uncertain. Just as space becomes a chaotic, fluctuating froth at the Planck scale, about 10 to the negative 35 meters, time might lose its smooth, continuous character at the Planck time, about 10 to the negative 44 seconds. Below these scales, our usual concepts of space and time might break down entirely. Some physicists think that time might not be fundamental at all, but might emerge from deeper timeless quantum processes. In quantum gravity, which attempts to unify quantum mechanics and general relativity, time is a major puzzle. General relativity treats time as part of the dynamic fabric of space-time. Quantum mechanics treats time as an external parameter. Combining these two pictures is extremely difficult. One approach is to eliminate time altogether from the fundamental theory. The Wheeler-DeWitt equation, which describes the quantum state of the entire universe, contains no time variable. The universe's wave function does not evolve over time. It simply is. Time emerges only when you consider subsystems within the universe and how they relate to each other. This timeless perspective is radical. It suggests that time is not a fundamental feature of reality, but an emergent property that appears at large scales. Just as temperature emerges from the average motion of many molecules, time might emerge from the relationships between quantum states of matter. If this is true, then the flow of time, the passage from past to future, might be an illusion. At the deepest level, there might be no flow, no becoming, no distinction between past and future. There might only be the timeless quantum state of the universe, a static mathematical object containing all moments at once. This view is deeply counterintuitive. It conflicts with our most basic experience of time passing. Yet some physicists take it seriously. They point out that the equations of quantum gravity seem to demand it. They argue that our experience of time might be like our experience of solidity. Solid objects seem continuous and unchanging, but at the microscopic level, they are mostly empty space with atoms in constant motion. Similarly, time might seem to flow, but at the fundamental level there might only be static mathematical relationships between quantum states. These ideas remain speculative. We do not yet have a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches all offer different perspectives on the nature of time at the quantum level. But they all agree that time at the smallest scales is likely to be very different from the time we experience in everyday life. The quantum realm reminds us that time is not as simple as our intuitions suggest. The smooth, continuous flow we experience emerges from a deeper layer of reality where time might fluctuate, where past and future might be less distinct, where the very concept of before and after might lose its meaning. Exploring quantum time pushes us to the edges of human understanding, where mathematics and philosophy intertwine, and where the familiar world dissolves into abstraction. The beginning of time. When did time begin? Was there a first moment? Or has time always existed, stretching infinitely into the past? For most of human history, these questions belonged to philosophy and theology rather than science. But in the 20th century, cosmology transformed into an observational science, and these deep questions became accessible to empirical investigation. The key discovery was that the universe is expanding. In the late 1920s, Edwin Hubble observed that distant galaxies are moving away from us. The farther away a galaxy is, the faster it appears to be receding. This is not because galaxies are moving through space away from some central point. Rather, space itself is expanding, carrying the galaxies along with it. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward, and the galaxies get closer together. The universe becomes denser and hotter. Continue this backward extrapolation, and you reach a point where the entire observable universe was compressed into a region smaller than an atom, with temperatures and densities beyond anything we can directly test in laboratories. This is the Big Bang. About 13.8 billion years ago, the universe emerged from an extremely hot, dense state and began expanding. In the first moments, the universe was a searing plasma of particles and radiation. As it expanded and cooled, particles combined into atoms. Atoms clumped together under gravity to form stars and galaxies. Over billions of years, the universe evolved from a nearly uniform sea of hot plasma into the rich, structured cosmos we observe today. The Big Bang is not an explosion in space. It is an expansion of space itself. There was no pre-existing space into which the universe exploded. The Big Bang happened everywhere at once. Every point in space was part of the extremely hot, dense early universe. This raises a profound question. What happened before the Big Bang? Was there a moment before time began? In classical Big Bang cosmology, the answer is that there was no before. Time itself began at the Big Bang. The universe does not have an infinite past. It has a finite age, stretching back to a first moment about 13.8 billion years ago. Before that first moment, there was nothing. Not empty space, not time, not matter or energy. There was no before. This idea troubles many people. How can time begin? What caused the Big Bang if there was no time before it in which causes could operate? How can something come from nothing? These are deep questions. Some physicists argue that they rest on confusion. If time began at the Big Bang, then asking what happened before is like asking what is north of the North Pole. The question has no meaning. There is no north of the North Pole. The North Pole is the point where the concept of northward loses meaning. Similarly, the Big Bang is the point where the concept of before loses meaning. But this answer may be too quick. Modern cosmology has become more sophisticated, and many physicists now think the simple picture of time starting at the Big Bang may be incomplete. One issue is that the Big Bang model, while extremely successful, cannot describe the very first moments. As you extrapolate backward to earlier and earlier times, densities and temperatures increase without limit. At some point, the equations of general relativity break down. You reach what physicists call a singularity, a point where physical quantities become infinite and the theory ceases to make sense. This suggests that the classical Big Bang model is incomplete. It describes the expansion of the universe from a very early, hot, dense state, but it cannot tell us about the origin of that state. To understand the true beginning, we need a theory of quantum gravity that can handle the extreme conditions at the start of the universe. Several ideas have been proposed. One is that the Big Bang was not the beginning, but a transition from a previous state. Perhaps there was a contracting universe that bounced at some minimum size and began expanding. Perhaps our universe budded off from an earlier universe through some quantum process. Perhaps time is cyclic, with the universe going through endless cycles of expansion and contraction. Another idea is that time as we know it emerged from something more fundamental. Perhaps at the very earliest moments, the universe was in a quantum state, where time did not yet exist as a classical concept. As the universe expanded and cooled, time crystallized out of this quantum foam, giving rise to the temporal dimension we experience. The theory of cosmic inflation offers a different perspective. Inflation proposes that in the very early universe, space expanded exponentially fast for a brief period. This expansion smoothed out irregularities and set the initial conditions for the Big Bang. Inflation theory is supported by observations of the cosmic microwave background, the afterglow of the Big Bang. In some versions of inflation, the process never ends. Different regions of space stop inflating at different times, creating bubble universes within an eternally inflating background. Each bubble is like our Big Bang, a region where inflation ended and normal expansion began. In this eternal inflation scenario, time may be eternal in some sense, even though each bubble universe has a finite age. These ideas remain speculative. We do not have direct observational access to the very earliest moments of the universe. The cosmic microwave background shows us the universe as it was about 300,000 years after the Big Bang. Earlier than that, the universe was opaque to light, and we cannot see it directly, but we can look for indirect clues. The patterns in the cosmic microwave background contain information about the earlier state of the universe. Gravitational waves from the early universe might carry information from even earlier times. Future observations may allow us to test different theories about the beginning of time. What is clear is that time, at least as we experience it, had a beginning. The observable universe has a finite age. There was a time before which no events occurred, no changes happened, no moments existed in our region of space. Whether this represents the absolute beginning of time, or whether there was something before that gave rise to our universe, remains one of the deepest unsolved questions in cosmology. The idea that time had a beginning challenges our intuitions. We are accustomed to thinking that every event has a cause, that every moment was preceded by earlier moments. But at the origin of the universe, this chain of causation must end, or loop back on itself in some way. The beginning of time sits at the boundary between physics and metaphysics, between what we can observe and what we can only speculate about. Time perception. While physicists study the objective nature of time, psychologists and neuroscientists study how we experience time subjectively. The way time feels is very different from the way physics describes it. Time seems to speed up and slow down. It feels like it flows. We feel embedded in the present moment, with memories of the past and anticipations of the future. How does the brain create this experience? How do we perceive time passing? One surprising fact is that the brain does not have a master clock. There is no single region that measures time the way a watch does. Instead, time perception emerges from the activity of many brain regions working together, each contributing different aspects to our experience of duration, sequence, and flow. The brain tracks time using multiple mechanisms at different scales. For very short intervals, fractions of a second, neurons in sensory cortex measure time through their firing patterns. When you hear two sounds close together in time, neurons in your auditory cortex fire in response to each sound, and other neurons detect the interval between these firing patterns. For slightly longer intervals, seconds to minutes, the brain seems to use working memory. Information held in working memory decays over time, and the amount of decay provides a signal about how much time has passed. This is why time seems to slow down when you are paying close attention. When your attention is engaged, more information enters working memory, and the richness of memories makes the interval seem longer. For still longer intervals, hours to days, the brain relies on memory consolidation. The number and vividness of memories you form during a period affects how long that period seems in retrospect. This is why childhood seems to stretch on forever. Every day brings novel experience that creates strong memories. But as an adult, when days become routine, time seems to accelerate. Fewer distinctive memories are formed, so in retrospect, the time seems shorter. This memory-based time perception explains many odd features of subjective time. When you are bored, time feels slow because you are constantly checking how much time has passed, creating many distinct moments. But in retrospect, boring periods seem short because few memories were formed. When you are having fun, time flies because you are not monitoring it. But in retrospect, fun periods seem long because many rich memories were created. Time also feels different depending on emotional state. Fear makes time seem to slow down. People in car accidents often report that everything seemed to happen in slow motion. Studies show that this is not because the brain actually speeds up during frightening events. Rather, fear creates intense memories, and the vividness of these memories makes it seem in retrospect that more time passed. The brain's construction of time includes the feeling that time flows, that there is a moving present moment that advances from past to future. This flow is central to our experience. We feel ourselves living through time, moving forward moment by moment. Yet, physics describes time as a dimension, a static coordinate. Nothing in the equations flows. Some philosophers argue that the flow of time is an illusion, a feature of consciousness rather than reality. They point to the block universe picture, where all moments exist equally. From this view, the passage of time is like the appearance of motion in a movie. The film itself is static, a series of still frames. The motion emerges only when the frames are viewed in sequence. Similarly, the flow of time might emerge only from consciousness processing the static structure of space-time. Others argue that the flow is real, that consciousness is somehow special, that the present moment has a privileged status. They suggest that physics is incomplete, that it captures the structure of space-time but misses something essential about temporal becoming. The debate mirrors ancient philosophical disputes. Is time like a river that flows, or is it like a landscape through which we travel? Does the present moment have special ontological status, with the past fixed and gone, and the future open and undetermined? Or are all moments equally real, with our sense of present merely reflecting our location in the static, four-dimensional structure? Memory plays a crucial role in our experience of time. We remember the past, but not the future. This asymmetry seems fundamental to what it means to be conscious in time. Memories allow us to learn from experience, to anticipate future situations based on past patterns, to construct a narrative of our lives. But memory is not a simple recording. Every time you recall a memory, your brain reconstructs it. Neurons that fire together during the original experience become associated, forming a network. When you later remember the event, this network reactivates. But the reactivation is never perfect. New associations blend with old ones. Details fade or are replaced. Your current emotions and beliefs color the memory. This reconstructive nature of memory means that our past is constantly being rewritten. The story we tell about our history changes over time, not just because we forget, but because we actively reshape memories each time we recall them. In a strange sense, the past is not fixed. At least, our access to the past through memory is not fixed. This raises questions about the relationship between psychological time and physical time. Physics says the past is fixed, unchangeable, part of the static structure of space-time. But psychologically, the past is fluid, constantly being reinterpreted and reconstructed. Which view is correct? Or are they both correct, describing different aspects of time? The brain also anticipates the future. Much of what the brain does is prediction. It builds models of the world and uses them to forecast what will happen next. When you reach for a cup, your brain predicts where the cup will be when your hand arrives, accounting for the time it takes to move your arm. When you have a conversation, your brain predicts what the other person will say, allowing you to respond quickly. This predictive processing is essential for navigating the world. It allows you to act in real time, despite the delays in neural processing. It takes a fraction of a second for sensory information to travel from your eyes to your visual cortex and then to the parts of your brain that plan actions. By the time you become aware of seeing something, it is already in the past. To act in the present, your brain must predict the present based on information from the past. In a sense, you do not experience the present. You experience a model of the present constructed by your brain based on recent past information and predictions about the immediate future. The present, you feel, is a synthesis, a best guess created by your nervous system to allow you to function in real time. This constructed nature of experience extends to time perception. The brain does not passively receive time. It actively constructs the experience of duration, sequence, and flow from fragmentary information. The seamless river of time you experience is an elaborate creation, assembled from neural signals, memories, predictions, and the brain's own models of how time should behave. Understanding this does not make the experience less real. It reveals that time perception, like all perception, is an interface between mind and world. The brain evolved not to represent reality perfectly, but to represent it usefully, in ways that promote survival and reproduction. Your experience of time is shaped by evolution to help you navigate the world, remember the past, anticipate the future, and act effectively in the present. Time's mysteries. Despite centuries of investigation, time retains its mysteries. Many questions remain unanswered, and some may be unanswerable. One enduring mystery is time travel. Can we travel through time? Forward time travel is possible. Time dilation allows you to effectively jump forward by slowing your clock relative to others. But backward time travel, visiting the past, is a different matter. General relativity does allow solutions that contain closed time-like curves, paths through space-time that loop back on themselves. If you follow such a curve, you could return to an earlier point in time. These solutions exist mathematically, but whether they can exist in physical reality is unclear. Most physicists believe backward time travel is impossible. It leads to paradoxes. The grandfather paradox is the classic example. If you travel back and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, you could not travel back to prevent their meeting. So, you would be born after all, allowing you to travel back and prevent their meeting, leading to an infinite loop of contradictions. Some have proposed resolutions. Perhaps the universe prevents paradoxes by making time travel impossible, through some not yet understood law of physics. Perhaps backward time travel is possible, but only to parallel timelines, not your own past. Perhaps the past cannot be changed. Any time travel you do was always part of history, creating a consistent loop with no paradoxes. These ideas remain speculative. No one has found a practical method for building a time machine. Even the theoretical solutions require exotic matter with negative energy density, which may not exist. Most physicists suspect that nature forbids backward time travel, perhaps through a principle we have not yet discovered. Another mystery is whether time is continuous or discrete. In our experience, time flows smoothly, but at the smallest scales, quantum mechanics suggests that space and time might come in discrete units. The Planck time, about 10 to the negative 44 seconds, might represent a fundamental quantum of time, a smallest possible duration. If time is discrete, then it does not flow smoothly, but instead advances in tiny jumps, like frames in a movie. Each Planck time would be a single frame, and the universe would evolve from one frame to the next. This would have profound implications for physics. Many theories rely on time being continuous, and modifying them to account for discrete time is challenging. We do not yet know whether time is continuous or discrete. At scales we can currently observe, time appears continuous. But our theories might need modification at the Planck scale, where quantum gravity becomes important. A related question is whether time is fundamental or emergent. Is time a basic feature of reality that cannot be reduced to anything simpler? Or does it arise from deeper, timeless processes? Some approaches to quantum gravity, particularly certain interpretations of loop quantum gravity and the Wheeler-DeWitt equation, suggest that time is not fundamental. At the deepest level, the universe might be described by equations that contain no time variable. Time would emerge only when you consider subsystems and how they interact. If time is emergent, then at the fundamental level there is no flow, no change, no distinction between past and future. There is only a timeless mathematical structure describing the quantum state of the universe. What we call time would be like what we call temperature, a useful macroscopic concept that does not appear in the fundamental microscopic description. This view is radical and counterintuitive. It would mean that time's flow, which feels so immediate and real, is an illusion in the deepest sense. The universe does not change or evolve. It simply is. All moments exist eternally in the timeless quantum state. Yet we experience time. If time is not fundamental, where does our experience come from? How does the illusion arise? These questions remain open. Another deep mystery is the relationship between time and consciousness. Does consciousness require time? Could there be consciousness without temporal experience? We only know consciousness from inside our own temporal experience. We remember the past, experience the present, and anticipate the future. Our thoughts unfold in time. Our sense of self is tied to our narrative history, the story we tell about our past and future. If time is emergent or illusory, what does this mean for consciousness? If the fundamental reality is timeless, can consciousness exist in that timeless realm? Or is consciousness inherently temporal, requiring the flow of time to exist? Some philosophers argue that consciousness is what creates the flow of time. Without consciousness to experience it, time would be just another dimension, with no special flow or passage. The moving present, they suggest, is a feature of conscious experience, not of objective reality. Others disagree. They argue that time's flow is objective, that it exists independently of consciousness. Consciousness experiences the flow, but does not create it. These questions touch on the hard problem of consciousness, the puzzle of how physical processes in the brain give rise to subjective experience. Adding time to this puzzle makes it even more complex. We do not understand consciousness. We do not fully understand time. The relationship between them remains mysterious. Finally, there is the question of eternity. What happens as time extends far into the future? Does time go on forever? Or might it end? According to current cosmology, the universe will continue expanding forever. Galaxies will move farther apart. Stars will burn out. Eventually, After unimaginable stretches of time, even black holes will evaporate through Hawking radiation. The universe will approach a state of maximum entropy, a cold, dark, nearly uniform sea of particles and radiation. This is called the heat death of the universe. It is the ultimate fate predicted by thermodynamics. In the far future, countless trillions of years from now, no more work can be done. No more energy can be extracted. The arrow of time loses its sharpness as the universe approaches equilibrium. What happens then? Does time continue in a universe at maximum entropy, or does time itself end when change ceases? Some physicists speculate that in the very far future, quantum fluctuations might create new regions of low entropy, sparking new Big Bangs. Perhaps time is cyclic on vast scales, with universes being born, expanding, dying, and being reborn endlessly. Others suggest that time in such a far future might become strange and alien. With no clear arrow of time, with no increasing entropy, the distinction between past and future might blur. Time might lose the character we associate with it. These scenarios are highly speculative. We cannot predict with confidence what the universe will look like in the inconceivably distant future. But thinking about time's ultimate fate pushes us to consider what time really is, and whether it can exist independently of change and events. All of these mysteries reveal how much we still have to learn. Time is a familiar part of daily life, yet it remains one of the deepest puzzles in science and philosophy. Every answer raises new questions. Every advance in understanding reveals new depths of mystery. Closing reflection. As we reach the end of this journey through time, allow yourself to settle deeper into stillness. You have traveled from the everyday experience of seconds and minutes into the abstract realm of space-time and relativity. You have contemplated the arrow of time and the growth of entropy. You have touched the strange flexibility of time dilation and the quantum uncertainties that blur the boundary between moments. You have looked back to the beginning of time at the Big Bang and forward to time's distant future. You have explored how your brain constructs the experience of time's flow, creating the present moment from fragments of past and predictions of future. Time remains mysterious. We have learned so much, yet the deepest questions persist. Is time fundamental or emergent? Does it truly flow, or is that flow an illusion? What happened before the Big Bang? Why does time move forward? Can we ever travel backward in time? These questions may not have final answers. They sit at the edge of human knowledge, where science meets philosophy, where mathematics touches mystery. But perhaps that is fitting. Time is the dimension we cannot touch. We cannot hold it. We cannot stop it. We can only move through it, moment by moment, always forward, never back. We live suspended in the present, with our memories trailing behind and possibilities stretching ahead. And yet, in these quiet moments, when thought softens and the rushing forward slows, perhaps we touch something timeless. In the space between breaths, in the gap between thoughts, there is a stillness that does not move. In that stillness, the past and future lose their grip. There is only this moment, eternal and still, beyond the flow of time. If you found peace in this exploration, if these ideas sparked wonder or brought you quiet rest, I invite you to like and subscribe. Your support helps this small corner of the internet continue, helps other seekers find their way to these gentle contemplations. Share your thoughts below if something resonated, if a question arose, if you felt something shift in how you think about time. For now, let everything fall away. Let the questions rest. Let time itself fade into the background. You do not need to understand it all. You do not need to solve the mysteries. You can simply be here, now, in this moment that never ends and never stays. The night is here to hold you. Time continues its mysterious flow, carrying you forward, always forward, through this strange and beautiful existence. Rest now. Let go. Good night.